Alright, so you're supposed to, in the standard diagram of the trefoil, count the number of tricolors. It's not too hard since there's only 3 strands, but you have to count the ones that you might think are sort of really obvious just by transmuting the colors around. Right, that gives you different ones. So you have to count the number of tricolors for this one, and then the question asks, now take 2 copies, and this is an operation we're going to talk about a little bit further today. So take 2 copies like this and do this kind of thing like this, right? And join that together. So you get another knot. So originally I had 2 knots, but you take kind of their sum and count the number of tricolors of this. Okay, so they'll get a different number, more than that one. And then if you do it with 3 copies, so if you do 3 copies here like this, find the number of tricolorings of that, and you'll get some number more, and you'll kind of spot a pattern that it seems like the number of tricolorings increases in a kind of nice way, like a nice function. Okay, so then the idea of this is that now you need to, in the last part of problem 1 for problem set 2, it says show the number of tricolors of any projection remains invariant under randomized moves. So I guess the point is these are all tricolorable. So how do you distinguish between them? So far we only know is it not tricolorable or not, right? If these guys are all tricolorable and we're trying to show they're different, because we think sort of that this should be more complicated than this and should be different, and this is more complicated than that should be different, because there's no obvious way to sort of simplify this or that. So we think they're different, so how does tricoloring help? Well, you can count the number of tricolorings, and you can show that, in the last part of the problem, you would show that you do a Reidemeister 1 move, or 2 move, or 3 move, right? The number of colorings remains the same. So this is a little bit trickier than what I did in class, showing that tricoloring is preserved under the Reidemeister move. So one thing you have to do is, let's consider a diagram that you colored. Let's say you have some coloring of one diagram, that's denoted by sort of a dot here. And then say you have another diagram over here that you colored one way. Now this way, this diagram you might have, just kind of a schematic here. Say you have a certain number of ways of coloring, right? A certain number of ways of coloring that are different of one picture. You have another picture that's obtainable from the first by a Reidemeister move. So I guess what you want to show is for each way to tricolor, when you do a Reidemeister move, there's a natural way to send this tricoloring to sort of a tricoloring of the new picture. For example, think about if it's a type 1 move. So as a type 1 move, what does it do? It either removes or adds a kink. What's an obvious way to tricolor the new thing based on the old thing? Well, say the move added like say it adds like a little kink like that. Well, whatever coloring you had here, there's a natural way to color here that we discussed, just keeping the same color on this whole thing. And that's like a function. It sends a tricoloring from it sort of picks out a color in here and sends it to a coloring of a different picture. So remember, these are different pictures. So you have kind of this function here. And then I guess the idea is, say you have 2 different ways of coloring this one picture. Say under some Reidemeister move like a type 1, are you sure that it doesn't somehow, because this method doesn't somehow send you to just one coloring? So if you have 2 different colorings, and given this new way of coloring the true diagram, does that give you 2 different colorings of that? So in other words, it's just sort of like a one-to-one function, right? The function is, the function I guess you would define, sorry to be a little formal here, but it's kind of, I think makes it clearer. So it's a function of, that takes tricoloring, say one diagram, say call it D1, to tricolorings of the other guy, the tricoloring of D2, I guess function. So D1 and D2 are related by whatever right-of move you're investigating. And I guess you're defining a function that goes from tricolorings of D1 to D2. Is that kind of clear? I mean, when I have a projection and I look at a tricoloring and I have another projection, and from this I somehow have some procedure to color the other one, that's a function, right? I have some way to color, someone does a move, and I'm like, oh, here's a natural way to color the resulting guy, right? So I can do that for any tricolor in here, it gets sent to a tricolor in here, right? So my example, for example, if D1 and D2 are related by type 1 move, that gives you this function. And so what you're trying to check is this function one-to-one, first off, right? Are two ways of coloring my original diagram, do those go to two different ways of coloring? And also, is every way of coloring D2 obtained by my procedure? If I do that, then I've created like a one-to-one correspondence, right? Like, however this works, it's sort of like that picture maybe you've seen when you study functions where you have sort of a one-to-one correspondence between two sets of like objects, right? So that's the way to show the numbers the same. That's how you show two collections of things are the same. If you have a way to make them correspond in a one-to-one way, right? All the objects, right, in these collections, if they correspond, right? Because if you only show it's a one-to-one correspondence, it might be that there's more colorings of D2. You have to show everything's obtained from D1 that way. And you have to do this for every move. Okay? So that's a little bit harder than what we did in class, but if you kind of go through what we did in class, you'll realize it's actually not that hard. That's problem number one, where by counting the number of tricolorings, you show that that's a sort of better way than just seeing if tricoloring or not. Because it lets you distinguish a bunch of stuff. And in particular, it lets you show there's infinitely many knots, because it'll show you that you keep doing this with n trefoils as n increases, and those will all be different, because the number of tricolorings will depend on n in one simple way. Okay, so for exercise 2, I guess there's one thing I should explain about the 5-coloring problem. So for tricoloring, we use 3 colors, right? That we called 0, 1, and 2. Right? The reason I picked those numbers is there's a nice way to think of tricoloring, which is that you can think of tricoloring as you assign 0, 1, and 2 to the different strands, and you use at least 2 colors, and the condition, so the second condition is what? They're all the same color or different at each crossing, right? So there's this condition at each crossing either only one crossing, one color appears, or all do. Now is the kind of important condition that's harder to satisfy. Well, you can describe it in terms of those numbers 0, 1, and 2. What you can say is, you can replace this by, if your strands are now numbered 0, 1, and 2, so let's say, let's call it like this, x, y, and z, right? So x, y, and z represent 0, each represent 0, 1, or 2. Well, you can write this little equation that should look familiar from the problem, right? It's, let's see, x plus y, right, minus 2z should be divisible by 3 in this case. Okay? So it looks, so in the problem, I have a similar equation, but I say divisible by 5 for 5 coloring. So I'd be like, so let's replace this condition is basically the same as this. So you might say this is not obvious, but what numbers, just run through all the numbers, right? Like if they're all the same, like 0, 0, 0, then is that divisible by 3?